Okay, hello and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving as a global membership of computing professionals and students. I'm Chris Pease. I'm currently a researcher at MIT Media Lab, where I lead the Agentic AI Working Group and lead the Decentralized AI Research and Venture Hub. I'm also the founder and CEO of AgentiCorp, building agentic AI systems to scale human and AI collaboration in enterprise. For those of you who may be unfamiliar with ACM or what it has to offer, here's some more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. You can see some of the highlights on your screen. ACM provides, for example, access to the ACM Digital Library, the world's most comprehensive database of computing literature, leading publications and global conferences that draw top experts on a broad spectrum of computing topics, support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards, and the ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. I'm sure you can join me in acknowledging the critical importance of this particular training program, Learning Center, and also the value add for us as we continue careers in a very fast-moving space. Before we get started, let's just quickly mention a few housekeeping items shown on the slide in front of you. If you have questions at any time, please type them into Zoom's Q&A button. We're going to try and organize the questions as Aditya speaks and get to as many as possible as we proceed. And so we're going to try and integrate that with the very technically dense presentation that we have here today, so we can intersperse and answer questions as we go. So if you can indicate that on Zoom, and we've got additional help for that. This session is being recorded and archived, so you'll receive an email notification following when it becomes available. And please check learning.acm.org for updates on this and upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. It'd be fantastic if you could just take a minute to fill it out and improve the Tech Talks to make sure the content that we deliver is the content that you need. Now, so today's presentation is the Dynamic Neural Network Compression for Scalable AI Deployment by Aditya Challapally.
Awesome.
Aditya Challapally is an applied science lead at Microsoft, where he focuses on building agent-driven systems, scalable reinforcement learning workflows, and model compression techniques for deploying large models on edge devices. He also leads the Connected AI group at the MIT Media Lab, where his research centers on edge-first AI architectures, decentralized coordination systems, and distributed learning. So Aditya, without further ado, let's take it away. Thank you.
Wonderful. Thank you so much, Chris. And thank you for having me, ACM community. So let me explain a little bit about what we're talking about today and why at least we think it's quite cool. So I was gonna please feel free to ask questions throughout, as Jan and Chris mentioned. This is a very technically dense concept, and we've tried to simplify it as much as possible into a simple website, and we'll send this out afterwards, which includes demos and things like this to make it super simple and easy to understand. So feel free to post your questions as we talk. Cool, yeah. So I guess the first question is like, what does this invention do, right, Chris? Like maybe we should start there. Yeah. And so let me explain a problem with running neural nets or machine learning based models on devices. So let's walk through this as an example. So currently, let's say you have a laptop and you want to run a large language model on your laptop. Let's just say, and it takes up 14 gigabytes. Let's just say. That means while you're idle browsing or you're actually doing work or you're going back to idle browsing, it's always running at 14 gigabytes of RAM, and you can't do other stuff, like you can't play games, you can't open other apps. Ideally, what you would want if you're running a large language model on your laptop is for it to be what we call ambiently intelligent, like it's running in the background constantly doing some task, but you want it to adjust how much memory it takes up based off what other work you're doing. So ideally, what you want in a dynamic memory system is when you're just idle browsing, for example. Um, Actually, let me take a step back. Typically, what you would have in a normal memory system is uh, a system that does vary how much memory different apps take up. So here, for idle browsing, if you have a service that runs 14 gigabytes throughout the day, then you can't run other stuff. Ideally, what you would want is a background system that varies how much space it takes up based off how much memory there is. So explaining that in terms of large language models, say you're doing idle browsing, let's just say, and uh, you're only using up, uh, let's say you're using up 12 gigabytes or 12 gigabytes or 10 gigabytes of RAM. Like your game takes up 10 gigabytes. You want that background process or the large language model to take up only 4 gigabytes of RAM. On the other side, say you're actually working on something that requires the large language model, then you want it to take up 12 gigabytes of RAM. You want it to take up more RAM. And when it goes to being idle, when you're not doing much work, you want it to go back to being 4 gigabytes of RAM. That's the ideal. And this is really important to understand because this helps set up the rest of this process and this conversation. We imagine a world for large language models where and for machine learning models in general, where they're running everywhere like software does. So right now, if you're running on a laptop or a smartphone or whatever, there's a bunch of software processes that run, and they vary their own memory based off what you're doing. Currently, we can't do that with large language models because they take up a set amount of memory. What this invention does or what this framework does, is it allows you to vary how much memory dynamically a large language model takes up in the background. So now you can run machine learning models on your phones, on your laptops dynamically. And that's the main problem for why we can't run them right now on edge devices. Any questions on that, Chris, or any questions from the audience on that?
We had a question coming in from Mirko. Is the problem solved by OS designers, what they've called long paging?
So, this is a good question. So OS designers, so this is solved for for operating systems a long time ago. And I work at Microsoft and we solve this with different subsystems and different services that run and manage memory and manage subservices. This doesn't work for large language models because large language models fundamentally to work have a set memory footprint. So they'll have like a 14 gigabyte or 16 gigabyte footprint. And if you lower them, they essentially don't work anymore. Like you can't, currently there's no mechanism to dynamically lower them. So it won't work with OS subsystem services right now. Does that make sense, Dr. Ludid? And uh, for the training will be slower to Mario's question. This is not about training. This is just for inference. So there's no training that will occur. It's just that influence will potentially be slower or faster, but we'll talk about that. But it does affect inference. Do those answers make sense to both those people? Okay. Yes, and so mostly asked this question, aren't all LLM providers solving this issue by releasing a lighter version of LLM? This is a great question. So the problem with this, yes, and Microsoft actually specializes in launching small language models. So the small large language models. So like the Phi model class is known to be the smallest, but also potentially the most performant model class of small model classes. But the problem with that is that if I go back to this diagram, the problem with that is that it always runs at 4 gigabytes. So it always runs, let me just move you guys over here. The small model will always run at 4 gigabytes. So instead of allowing it to expand when you want to use it more or when a bigger task comes in, you'll always have to use it at 4 gigabyte and it will always take up that 4 gigabyte. It won't ever go to 0 necessarily or even smaller than that. So the trade-off you're making is that when you use a small large language model, which are great, you potentially don't get the benefit of using a bigger one when you need it. Does that make sense, Mohsin? Okay, well, you can let me know you can let me know if it's been answered or not. But okay, Alex has a question of, does this invention manage GPU RAM, CPU RAM, or both? So this system doesn't care too much about GPU or CPU. It's more of a system for affecting the neural net model itself the um rather than talking about which system it runs on. So we'll talk about that later. And Ankit asks, how about using low bit precision? That's exactly how this system works. Um, okay, cool. So let's dive in. So as I said, there's some fixed memory problems, which is that the background AI agents hog a certain amount constantly, and you can't afford always on LLMs on edge devices. So you can't always say, hey, my small language model will just run to the point all the time because it could just take up a lot of battery if it's just constantly running in the background. Um, okay, cool. So then how this solution works, and we'll walk through this carefully because it's it can be quite intense. Chris, do you have anything to say about the invention or anything like that? And by the way, Chris, for everybody, Chris is an expert in this field as well. Chris leads a lot of edge work at MIT. He leads the agent platform work at MIT, and works in this space in industry as well. Chris, anything to say on this?
Yes, yeah, no, I'm really interested to see kind of like, so this is something we can run locally on device as we move towards many more agents being run at the extreme on edge devices, and then we consider networks of agents. We want
Exactly.
to know like how does this impact the agents running on device?
Exactly. So for folks, why this, again, just to stress on why this framework is important is, imagine a world where every single edge device, so right now your fridge, whatever, your phone, your thermostat, etc., runs software processes in the background. Imagine a world where in the new for to run machine learning, you would need to go to the cloud and do all this work. Imagine a world where it runs machine learning on its own device. So and that's the world where we're going to, where it uses ML to make its own decisions and then act on those decisions. And this would be a critical part of that because currently we can't just have machine learning models running indiscriminately in the background. It would take up too much battery, too much space, too much memory. Cool. So let's talk about what the um uh yeah, if you have any questions, please post it in the Q&A and not in the chat. Cool. So in terms of the solution overview, let me walk through it really quickly and we'll go through it a few times just because it's a little complicated. The first one we do is we do an offline analysis where we identify which layers can be compressed. And we'll talk about what that means. And then we generate a file um, on which layers can be compressed. And then we send that with the model. And then during runtime, the CPU compresses those specific layers or acts on those specific layers to compress the size of the model, and then it also restores the model weights once we need a bigger model. Any questions on that, Chris?
And so what's really kind of inspired that kind of this movement here, kind of to go to this sort of like this partial reduced footprint. It sounds like it's kind of a flexible footprint that we can tap into when we need to, but pull back from when we need some resource for something else.
Yeah. Well, yeah, I mean, what really inspired it was that, and I guess this is one of the questions from Cruz Romero is we want to dynamically scale the large language model depending on the task and memory necessary to execute said task. Yes, so there's two options, or there's three options right now for people to run large models on their own edge devices or on their own laptops right now. They can run a really large model and have it take up a lot of memory, and that means they can't run other apps, so they will just have to run that large language model. The second one, and then potentially sort of just disable it or sort of close it down once they stop needing it. The second one is to constantly run a small large language model in the background, and that takes up a small amount of space. But the trade-off there is that you won't potentially get the benefits of running a large language model. Like you won't potentially get better answers and all of that, especially when you potentially need those. And so this is a compromise between those. So this allows you to run a large language model that is actually large when you need it, and also scale it back to something that's small when other memory needs come up. Does that make sense for folks?
So can you walk through kind of how this works in practice?
Yes. That's the offline analysis I was talking about. So in the offline analysis, what we do is we run a bunch of these calculations on what layers can be reduced, like what parts of the model can be reduced and have minimal effects on the end accuracy. And then we document all of that into a file, and then we send the file with the model, and the CPU compresses those specific layers while the model is running. And the file that we send it is called the automatic decompression instructions file. Does that make sense, Chris?
Yeah. No, I think it'd be great to if you can sort of walk through this from end to end. Then that'll probably answer some questions ahead of time. So let's go through that end to end. Yeah.
Certainly. So it generates this file, and just so that anyway, so let's talk about let's go through a demo potentially that would potentially help folks understand this better. So this is a complicated setup, but let me explain what it is one by one. We're gonna walk through a neural net where there's only 8 layers. So there's 8 layers to this neural net. Usually imagine there's like hundreds, if not more. And so there's only 8 layers and there are very few weights. So right now, let me say that we want to run this model at 50% of the memory of this edge device. Okay, so right now, this model runs at 50% of the edge device memory. Let's say as we go up in terms of memory, so as other apps use more memory, what happens is we start to reduce the amount of memory each layer takes up. So you can see here, if this was the original, the current takes up that much less memory. That also means that our accuracy does go down, but our accuracy would have gone down anyways if we had used a small large language model. And let me take this to the extreme. As we increase our memory even more, you drop the memory that each layer takes up even more, to the point where potentially we even stop using some layers. But obviously, as you can see, the accuracy goes down significantly. Similarly, our speed also goes down by quite a bit. So our speed goes down to 30% of what it was before for a bunch of other reasons that have to do with subservices and subsystems. But so again, just to review that, as the edge device as other apps. So if you're on your laptop, if you're running multiple different apps and you start to use them more or even open more apps, then we start to do these compression work, which we'll talk about and how it works, and the memory that each layer takes up goes down. Similarly, the accuracy also goes down by quite a bit. Cool. Um, okay. Hey, okay. Then let's go through some questions. So, um,
So we did have one question. What does it mean to compress a layer?
great question. So, I'm going to explain that in a second once we go down here, and we're going to talk about what is the compression process in a second. So I won't talk about that. I'm going to explain that in a second. And we're also going to talk about what different techniques we use for compression. So we're going to talk about that. So, um, yes, and it seems like a lot of people are getting to that question. So let's dive right into it, actually. So, um, the important thing to note before we forget is that there's three layers of compression: quantization, layer fusion, and then pruning. I'll explain what each of those means, and then we'll talk about layer fusion and then pruning. So then this is what a normal neural net would look like. Okay, so and there's different levels of precision that we use. FP32 describes the level of precision, which means like how many decimal places are there in each weight. So in this case, this is a layer, okay? So this is 0.782, negative 0.56, etc. All these numbers are one layer, and this is another layer. When we say we quantize, what happens is we reduce the number of decimal places that show up in each weight. So this is 0.782, it goes to 0.78. It doesn't always mean that we round up or down, to be clear. It just means that we just reduce the number of decimal points, and we get that during that offline training, which we send in that .audi file. And so we will say to the model, hey, in this case, for example, what we've done for these two layers, and this is the first and second layer of this model, just drop the last one. Just drop and round up. So the 0.123 goes to 0.12. If we want to quantize it further, or if we want to make this model even smaller, what we do is we then drop all the decimal points and we just use straight numbers. And to make sure that the model still comes out with the right values, in this case, if we further quantize it into 8, which is a different form of determining how much accuracy and precision there is, then we have to use completely different numbers. Like instead of 0.78, we use 199. Instead of negative 0.46, we use 117. And so that's what these models, that's what the .audi file contains in terms of instructions. Okay, cool. I'm going to take a pause there and answer a couple of questions. And a lot of these questions we're going to answer soon. But it seems like we've answered a fair few of these. Chris, do you have any thoughts, or do you think any questions are particularly interesting to answer?
Yeah, I think like how do you choose what to quantize, which layers?
Yes. Okay. So that's what we determine in this offline analysis. We identify which layers can be compressed with minimal accuracy loss. So let me so let me show you what this .audi file looks like. And I just want to be super clear. I didn't name it .audi, my colleagues did, and I'm very flattered by that. And so Chris also knows that. So the
Yeah.
uh but it is my name, but I did not name it, to be clear. But the in this .audi file, which is sent with the model, we see, so here for example, we'll say, hey, for the compression tiers, there's three tiers that are really important: critical, important, and expendable. The expendable ones we want to act on immediately. So we'll say for these attention layers, you can act on them right away. And then these are the actions you can perform, which we'll talk about in a second. But let me show this potentially visually as well. We identify three things: critical layers, important layers, and expendable layers. So this we do through offline analysis, saying, hey, if we change these values, how much does it affect the end result? If we change these values, how much does it affect the end result? And so if there's 100 layers, we classify each layer to a critical layer, important layer, and an expendable layer. And so we say, hey, for the critical layers, we have to keep them at the highest precision all the time. For the important layers, we can potentially reduce their precision and go to the FP16 piece that I was talking about. For the expendable layers, we can take them to int 8, which is like the almost no decimal points. So in fact, going back to the compression demo, in fact, somebody asked, potentially why does layer 7 just disappear? So in fact, you go here, all of these are at full weights, and then as you go up, the layer 7 goes completely away because we've identified that it's an expendable layer. And once we get to the pruning stage, we can just take it away. Cool. Okay. Any questions on that, Chris?
Just going through. To this one. How does dequantization work? That's a question from Michael.
Okay, nice. Yes, okay, nice. So how we work backwards is actually in decompression. But let me finish talking about compression first, and then I'll
Okay.
quickly go over
Yep.
compression, and then we'll talk about decompression and dequantization. So there's three methods to compression. There's three steps: quantization, layer fusion, or delta work, and then pruning. So then this is the delta work. Really quickly, actually, how I can explain how dequantization works by diving into quantization a little bit more. What we have is a delta storage system. So we have the current weights, the base weights, we store the difference, and adding them up, we can get to the FP33 weights. And so let me explain this really quickly. So we have these quantization analysis. So we calculate precision loss per layer. We store the differences, and the advantage here is we can say, instead of storing specific differences, which maybe would take up a lot of space, we can just say something like, for this layer, roughly, just reduce all of the decimal points by 1. And that's fine, and round it up, and that's fine because it's an expendable layer. It doesn't matter too much for increasing accuracy. And then we create a lookup table, and then we rapidly combine the compressed weights when the deltas are needed. So, for example, if these are all the different layers, some layers won't have significant delta values and some will. Okay, you know what? Somebody asked a really important question, which is, how do we identify which layer can be redundant, and how much redundancy can it have? What's a critical layer versus not a critical layer? So this is actually a limitation of this framework. Let me first say that it doesn't work super well on really large and complicated machine models because we can't do this specific layer analysis. But so this is just a path towards that for now. But what we do is you can identify potentially by turning off some layers and figure out what is most valuable and not valuable. So let me give you an example. In a convolutional neural net, you can have multiple convolutions to get to a point where in a convolutional neural net you'll use for image identification. And there's a step called convolution. So there's multiple steps called convolution. And each convolution is potentially either looks at a certain feature, or it takes the image and it compresses it to something that it cares about in each layer. So for example, if it's a dog, then a convolutional layer, and I'm super simplifying here, we'll say oh, like, um, I'm really focused on like the face of the dog. So that's what I'm gonna focus on in terms of a neural net, and I'll sort of get towards that stage. You can say potentially, and I'll try to find that or something like this. You can potentially say, potentially the face of the dog doesn't matter so much. So I'm just gonna turn off that convolutional neural layer. Like I don't need that layer, and I can still get a lot of accuracy without it. So things like UNet, for example, have a lot of layers that go down and then back up. And so you can just say, I'm going to just turn off two layers. I'm going to lose a little bit of accuracy, but that's okay. Um, and that's how you would identify roughly. Okay, do these layers generalize to different types of architectures or no, they don't, which is why you have to do this offline analysis per model. Um, and it takes up a lot of time to do it per model because you have to very carefully identify what you can generalize, what layers can go away, how you have to change the other layers every time you change one layer, and that takes up a lot of work. Okay, so then um, let me explain really quickly uh, what how layer fusion works. Ooh, actually, I'll go up. I won't go through any of the math, but as I said, there's a couple of steps um, that we go through. It's quantization, layer fusion, and then pruning. So what layer fusion does is, again, talking about a convolutional neural net, if you have a convolutional layer and another layer, we potentially say, let's just fuse that, and then we just have one convolutional layer. Um, Okay. Peter asks a great question. How does reducing the decimal points result to smaller memory usage? Great point, Peter. So just reducing the decimal points like this for a small layer doesn't reduce it that much, to be honest. Like in this case, we're just talking about reducing it by 1 point. This is just to illustrate. Usually you'd be reducing it by quite a significant number of points. And oh, exactly. Actually, Camilo answered it. Camilo answered it great in a great way. You know, just so everybody can read his answer. Um, Peter's question is, how does reducing just a few numbers in this decimal point affect the memory that much? And the reduction is a side effect of using floats um, versus integers. So in lay terms, FP16 is a float representation, and FP16 implies 50% less memory. So FP32 uses 32 bits and FP16 uses 16 bits. So that's 50% less memory, and int8 uses 8 bits. And so Camilo, that's actually a very wonderful answer. So thank you for explaining that. Okay, Chris, any questions before I go to the decompression work? These are really good questions, by the way.
Yep.
These are and honestly, there's some good answers in the chat as well to those same questions. But
Yep. No, I think we should carry on through.
okay, cool. Okay, cool. So, oh, and folks who are asking if there's a preprint of this work or something like this, uh, no, we may consider doing it, but we just implemented this at Microsoft, and so this was reasonably proprietary up until recently when ACM sort of wanted to do a talk about this. So, and now that we've established it and we're working towards it, we might publish it. But I also want to acknowledge that this is still very early days. There's still a lot of problems with this approach, but it is a very novel approach to solving what is a very difficult problem. Cool. So, let me explain. So for decompression. So to be clear, when we would only decompress when we say, hey, we want this model to be running at a larger capacity. We want the larger model to be running because we need more accuracy or something like this. So we first consult the .od instructions and we say which layers to restore first. And the answer is something like the attention layers 0 to 5, and then we store potentially their embedding weights. Then we load those instructions or those delta values, and then we apply the restoration. So the restored weight is the compressed weight plus the delta. And this gets it back to us back to full precision. Um, so the quick math, for example, to go from int 8 to FP16 is the restored value is the int 8 times the scaling factor, which is stored in the .audi file, plus the stored delta. That's just an example. And we would do that across the critical, important, and expendable layers. So for the critical layers, we've always kept them at FP32 because we really need the high level precision for them. For the important layers, potentially they're back to FP16. They were at FP16 and potentially we take them back to FP32. And the expendable layers, we potentially keep them or don't keep them depending on what the .audi file says for how much accuracy we need to get to. Okay, cool. Let me answer some questions then. Um, uh, Chris, do you have any specific questions that you think are interesting from what people are saying?
So yeah, there's one sort of how the community can. I'll read the question is the community considers that there are no really reliable types of benchmarks to reliably compare LLMs. And so how do you reliably compute accuracy of the models when deciding which layers are
Great question. Okay, great question. So this boils down to a very important question of how do we determine accuracy? And so let me again, for folks who maybe not understand what the question is, for example, we have this here piece, we have this number here that says 99% accuracy. And we say, quantization takes us to 80% accuracy. And the question is, we can't even compare models generally between each other. How are you comparing a smaller model versus a bigger model? We have an advantage here in that we know what the answer comes out to when we know it's a full model at 100%. So we know that. We know it's 100% accurate at when it's at its largest size. And so we're not saying it's 100% accurate in terms of the world. We're just saying it's that's the benchmark we're going to compare against. That at the largest it can be as a model, it's 100%. Then when we start to reduce the model size, we can start to compare the answers it gives to its own previous answers when it was a full model. So we'll ask it something like, so we have a set of questions, a set of 1,000 or whatever. We have a large data set of questions we ask it. And then we ask it the same questions when it's a smaller model. And then we can judge how many of them it gets right versus it gets wrong when it's a smaller model. And that's how we determine accuracy here. Does that make sense? Like how many it matches up to the large model versus how many it gets wrong now. Okay, cool. Does that make sense, Chris? Do you think that
that sounds good? Yeah, thank you.
anything else? Any other questions? These are really good questions, so I think I'd love to spend more time on them.
I have one of my own sort of when I think about the applications of agents and increasingly that application of agents being on edge device and potentially needing exactly this type of solution, the kind of the construct that a lot of LLM-based agents now are using to effectively kind of refine their model in a particular way for a particular application for a particular agent. That's kind of how can we push that requirement, if you like, through this type of process to establish the compression? Does the compression impact particular agents maybe more so than other agents because they're using a different piece of kind of knowledge space, so to speak?
Yes, 100%. So, what's interesting about this is we have to do this type of work where we find which layer is expendable versus not expendable or whatever, like what we can change per model every time. And
Yep.
that's like it's an incredible amount of work. And as I said, there's a lot of limitations in this in that it can't necessarily scale to large models just yet because it's so hard to do. We don't even understand how large language models work entirely, so it's hard to do it at scale. So as we scale this to different agents and stuff like this, like a research problem that is very important that we'd have to tackle is how um, how would we do this and scale this across different large language models and different agents? Because you're right, like it would be completely different per model, per agent, per task, etc. Yeah, and so to be honest, there's no current answer to that. Yeah.
Okay. Yeah. So interesting research problem for everyone on the call.
Yeah. Absolutely, yeah. Cool. Any other questions that you think are interesting from them? Yeah. Oh yeah, so Dr. Lued also asked us, do you do analysis and compression ahead of time or just in time while running the LLM? So the key innovation here is that we do the offline analysis and then we pre-analyze which neural network layers matter the most, then create the .audi files, and then tell the system what to compress and store the model. So we do that work ahead of time. So this offline analysis happens ahead of time. We store those instructions in the file, and then the compression happens dynamically based off the stuff in this file. And this is really an advantage for um, potentially edge devices or like laptops, for example, that have a lot of hard drive storage, but very little RAM, like very little rapid access memory storage, because they can store a potentially large file and dynamically change the weights using the limited amount of RAM. Okay, does that make sense, Dr. Led? Okay. Um, Charles Denoff asks, if I'm following correctly, will this dynamic compression also have positive environmental impacts because less energy will be used for AI models globally? You know what? I would say I would hope so, but I really doubt it, to be honest, Charles, because in the future, I think if we solve a few of the limitations associated with this research, where uh, we potentially have more the ability to compress even larger models, then yes, then I think it would potentially solve it a little bit. But one of the problems we have now is that a lot of our machine learning work is processed just through a few data centers rather than using a lot of the capabilities we already have in our laptops and our phones. And so it would potentially allow us to have more intelligence in the world, if not less energy. Okay. Uh, any other questions that are interesting, Chris?
Um, so, how much if you like kind of switching? Is this kind of obviously there's the dial that can be dialed up and down. How to what extent is it sort of predictive and for how long? So once you started using this compressed version, uh, um, and then there's an additional process running that's needing resources. What prediction is there in terms of how long that additional process needs those
Right.
resources? When at what point do you scale up? Do you anticipate if it's a particular
Yeah.
process that's running? Is it
Yeah.
Yeah.
So so we have a tab called resource monitoring, and there's a constant dashboard that's running internally where we think about like how much memory usage, how much CPU load, how much temperature, and how much battery. And so we constantly pay attention to these things to dynamically change the model size. And potentially, there's a world in which uh we can talk about it afterwards in case people have questions, but there's a world in which like instead of just quantizing and requantizing or updating the precision or things like this, all we have to do is just load a big model, take it off, and load a really small model. People also can think of it like that. But in any case, we as we look at these dashboards, we dynamically adapt. And the advantage here is we don't necessarily need to predict too much ahead of time what size the model needs to go to, because it can have this compression and decompression happens so quickly, at least on systems that it's optimized for, like using Windows subsystems or things like this, that we don't necessarily need to predict. We can just say, there's a low battery mode and there's a high performance mode, and we can automatically go like change the model size in a few seconds. But we can talk through the math of that, but it can get a little complicated. Does that make sense?
Yeah.
Yeah. Yes, Tanya, Aditya answered your question correctly in that to do the offline analysis and generate the .audi files, you don't need to increase inference time. That happens offline. So it doesn't affect inference time at all, except for the time it takes to switch between different model sizes. Sorry, and go ahead, Chris. What else? What other questions do you think are interesting? There's a lot of questions, so feel free to pick any of them.
Has this approach been used with other architectures, other use cases like CNNs and GNNs?
It's a great point. So actually, the models that it works with well right now actually are actually CNNs and GNNs and things like this because it's very easy to disassociate different layers and understand how much value each layer has. Like for example, in a UNet or something like this or a ResNet, we can say, hey, these are the different values that matter a lot here. And potentially this is a layer that matters a little bit more. For more complicated architectures that use transformers, this work is actually very hard to do because um, attention matrices are so complicated and we still don't fully understand how they work, especially across different layers. So it's really hard for us to say, oh, a certain layer just doesn't matter. We could potentially say a certain layer doesn't matter for a certain type of task, like just reducing something like layer 7. But right now, this one of the research limitations actually is that it doesn't work well for transformers. It works well for um, other types of neural nets. So it's a good question. And one of the things that that people can think about is, how would you apply this to transformers? Because currently it does not work super well. Yeah.
And is there a ballpark uh, size of model that you found this to be particularly good for? I'm thinking kind of across the range of what's considered edge devices. At the very small end of that, there may not be. They may start with already a very small model rate, and so there's less scope to pare that down further, and so that might
Yeah.
impact kind of. It might mean that it's much more natural to apply this to particular classes of edge devices.
Yeah, so what's interesting is that the things that apply that this runs the best on are phones and laptops. So specifically because let's say it's around a laptop, like laptops generally have anywhere from 8 gigs to 16 gigs of RAM, and we found that range works really well for stuff like this because we can compress a model from being like an 8 to 10 gigabyte model down to 4 or 5 and still come up with reasonable answers um, that still run in the background. So that's a good question. Yes, like currently to your point, like if we have an edge model running on like a thermostat, for example, and it needs to determine, it needs to predict ahead of time like what temperature it's going to go to or something like this. The model's already small enough. It doesn't need to potentially compress that much more. But actually it does work really well on those sizes as well. So it works reasonably well on the 8 to 16 gigabytes, but it also works super well on like something that has like zero point 0.5 gigabytes of RAM.
Okay. Yeah.
Yeah. Because
And
we can go from 0 to zero point 0.5 pretty well.
and actually switching across now, is the compression process done in parallel or serially?
Great point. It's done up in parallel, not serially, because we can act on different layers independently. So if we go here, um, you can see that all of these go down se separately in many ways. So and in some cases, if you look at some of the bars, some of them actually go up. For example, if we look at layer 7, some of these bars actually go up when layer 7 goes away because we need more precision in other levels to still keep the same level of accuracy. And so it's all done serially, which we can do. It's all done in parallel, which we can do because all of the layers are independent in that sense.
Yeah.
Um,
And there was another question. You mentioned before that it doesn't work, that you found it doesn't apply so well to the transformer models. Do you know why that's the case?
yeah, so transformer models are very difficult to sort of independently analyze which layers are the most important versus how they're not important. And um, because we still don't fully understand like how they would work necessarily, like what the internal workings of them are versus that is we do know how that would roughly work for other types of neural net based models like CNNs or GNNs or whatever. So for folks who potentially don't appreciate or don't know how complicated a large language model is, especially modern ones, um, there's hundreds of attention matrices or maybe even hundreds or thousands or hundreds of thousands depending on the size of attention matrices that all feed into each other and they're all working different layers. So we can't just say, hey, we could just reduce some quantization, some weights for one layer, like for some 10th layer or something like this, and some 20th layer, because that'll completely change the answer. We might not even get English on the other side. And so that's why it's really difficult because there's so much interdependencies that we don't even understand yet. Yeah.
Good. Is the switching cost-worthy when the switch occurs frequently on most of the models? So a naive, the question was a naive example. If you run 10 inference iteration, is it worth it? But it's not worth it. But if you run 1,000 inference iteration, that maybe that one is worth it. How does that match?
I'm actually not sure if I understand the question, Chris. Do you know?
Kind of the switching between kind of using the compressed version or not. If there are only so many steps that are being used in inference, so if it's just a 10 inference step,
Oh, I see what you mean. I
then
see what
it's
you mean. So,
maybe more or less
so
worth the
this is just
switching
an
cost.
example. We don't so this is just an example of 8 layers. This works on like 100 or 1,000 layer piece of model, so
Yep.
it's still very much worth it.
Yep.
All I'm saying is it's not worth it's hard to do on transformer based models, but we are researching it and potentially it'll be possible. The um the part that's interesting is that it is very much worth it because an example right now of running this on a laptop is uh, CNNs and GNNs and other neural net based models are still very helpful still very helpful in the background. And so um, you can automatically have it do sort of certain vision tasks or really easily just in the background while you're working or even act on your behalf while you're working. You just may act slower when if it's a smaller model, potentially have slightly lower accuracy, but it's still a very interesting thing to do and have so that it constantly runs in the background. And in terms of like, is it worth it to have a smaller model or not? The cost is minimal to decompress and compress it. So there's almost no cost. You'd rather just to have always on ambient intelligence in the background anyways. And hopefully soon this is a framework that hopefully will apply to transformer-based models, in which case the possibilities are much more exciting. Yeah.
I'm just going to try and I'm conscious of the time. I'm just going to see if we can pull out. So what's your optimization target KPI when deciding to use a tiny compressed variant or the full extent variant of the model?
So what we base it off of is this resource monitoring dashboard. We always monitor how much memory the edge device has, what CPU load it is, and then we decide between a potential low battery mode, a high performance mode, or something like this. And so the thing that we're optimizing for, the KPI we're optimizing for, is memory. Um, yeah. And
Uh,
so
yeah,
yeah.
go ahead.
No. Go ahead, Chris.
We just had a quick, given the time, we did a question, will the recording of the talk be available? Yes, it'll be available and that'll be emailed out from ACM.
Yeah. But yeah. I mean, do you have any closing thoughts on this, Chris? Especially as sort of an edge expert, edge AI expert, and neural net expert yourself at
Yeah,
MIT.
I mean, I think this is fascinating because it kind of makes this ability to contract and still provide some solutioning, some inference under different loads. I think that's going to be critical as we push more of that inference to edge devices. In particular, kind of my interest is on the agentic side of that, and I think this will be really interesting to see how we can measure the performance of that and what's considered to be proprietary in terms of kind of measuring that performance in a sort of proprietary compliant manner. It's going to be really critical as we kind of move forwards. But I think we can all see the future where a lot of software is fundamentally redesigned as an agentic kind of interaction. And so this type of interaction, this type of compute inference in smaller units in different parts of this system of the network is going to be increasingly critical. So really appreciate that. I think given the time, so I guess I'd like to just first kind of join everyone else and to thank Aditya again for the informative presentation and insightful answers. I know we've got a number of questions that we've not been able to get to. The talk will be recorded and sent out. In addition to that, there'll be a quick survey to suggest on future topics, etc. But we will take a note of the additional questions, and Aditya will be able to answer those and get those circulated as well.
Yeah.
Thanks very much. And on behalf of ACM and Aditya and myself, Chris Pease, thanks for joining us. I hope you'll join us again in the future. This concludes the talk. Thank you.
Cool. Awesome. Bye.